Hello everyone. So we are going to solve this problem, heat transfer in thermodynamics. So we have we have this problem. A metal shed standing on open field. We're given information about the dimensions of the shed and the heat transfer properties of the shed in terms of thermal conductivity. So we know that outside temperature, and we also know that rate of heat transfer. So we want to figure out what's the temperature at the inside of the shed wall, and how do we know that this heat transfer problem is talking about convective heat transfer and not a different type of heat transfer. So look at what the question is asking, where ask what the temperature at the inside of the shed wall is. So right now we know we're talking about the inside of the wall, not the air inside, which would be a convective problem because air is fluid and convective heat transfer deals with fluids. So right now we know we're dealing with the wall. We're also given the rate of the heat transfer through the wall, that's from one side of the wall to other, and so that's through a solid. Since we are dealing with heat transfer through a solid, this is a conductive heat transfer problem. Well, start this problem by drawing our diagram. Our importance for sorting information you're giving. So now we're going to draw the diagram. The diagrams are important for sorting out all the information you're giving and figuring out which way is the heat supposed to be going. Alright, there's our shed. So that's our shed. We know the outside temperature is 32 degrees, but we don't know which way the heat's going. We don't know if the inside of the shed is warm or cold until we look and see that that 270 kilojoules of heat are transferred through the wall to inside. So the heat transfer is going this way. That means since our heat transfer equation from the perspective of the inside of the object we're looking at, we have a positive Q because heat is going into the shed. So we know acute positive that shed is heating up. Therefore, the inside temperature should be lower than the outside. Here, you see that I put the above. The outside temperature, otherwise we couldn't get heat transfer into the shed. It would be going out of the shed. So again, Q is positive. We have heat going into this shed. In terms of the dimension we are given the length of the wall here, and the height of the wall, and we are given our wall thickness. We don't know anything. That's the wall thickness here. We don't know anything about a rooftop on the shed or the floor of shed, but that's okay because we're told to ignore the heat transfer through the ground, and the shed roof is, we're gonna skip that for now. Let's write down our heat transfer equation. This heat transfer equation is the Fourier equation for heat transfer, we are going to assume that heat is being transferred one-dimensionally through the thickness of the wall, because the wall is big enough that heat transfer is faster through thickness of the wall than it along the length of our up and down light. So we're going to type it now. Alright, so that's our core equation. Notice we have the negative sign in front of our K thermal conductivity. That's to make sure the heat transfer goes the right way. Delta X in this equation, the wall thickness is always negative because of where we set the 0 point for X. So now when you're going where you're doing this, delta X is always negative. That means the sign on Q is controlled by your tol minus Ti term. If To is bigger than Ti, like it's going to be in this particular example, then Q is positive and heat is flowing into the area. If Ti is bigger than TOQ is negative and heat is flowing out the area, the negative just tells you the direction of the heat flow. We have most of the information needed to solve this problem. We have Q, we have K, the thermal connectivity, we have delta X, the wall thickness, but we need to figure out is the area of heat transfer. This is the area the heat is transferring through. We're given the dimension of shed and we're told to ignore the ground and ignore the roof. For walls typically make up as a shed, so we have heat being transferred through 4 walls. Those walls have a length and a height, and that's the surface area the heat is being transferred through. So our area equation ends up looking like this. So I already typed all the information here and the answer, so I'm going to explain you the rest. So the equation is like the equation looks like here. Yeah, each wall we have multiply length times height to get the surface area. We have 4 walls, so we're going to put 4 out here out in front. That takes care of our area. All right, we are all set. We have everything you need to solve the problem before start plugging in numbers, though. Let's rearrange to get Ti by itself. So let's start, and that's here it is. That's the equation that I'm talking about. And so and this and this, there you go. That's the 2 equation that I'm talking about. So we go now. Ti is by itself now. Now we can plug everything in and solve for Ti. Let's do it. Okay, so let's substitute all the value here. Ti 32 plus 270 times 1000 times 0.011 over 4 times 2.4 times 2.5 and times 1.7, and up here 1 over 1 divide 60. So the answer for that is 27.1 degrees. So let's point out a couple things that I did here. So first, that 270 kilojoule of heat transfer every minute needs to get converted to watts. We're in kilojoules and we need to go to watts. So to go from kilojoules to joules, I multiply by 1,000. Then because 270 kilojoules are transferred every minute, not every second, and watts is joule per second, I need to divide by 60 here. See that? To get the term correct, when you do the Q is equal to 4,500 watts. 4,500 watts is Q. Notice. Now we need to convert the wall thickness to meters. So this is the converting the 1.1 centimeters to meters. And here, this little negative sign is because remember delta x is always negative, so you have to put a little negative sign right there to make your number come out right. Otherwise, TI is going to be bigger than TIO, which is not possible because Q is positive, therefore TI is smaller than TIO. So just remember those couple of tricks. So make sure your units are consistent with this problem. If you're not, you're going to end up with some very odd heat transfer rates or very odd thermal conductivities or odd temperatures. So that's all. Thank you. Let's box our final answer for this problem. Yeah. So thank you for watching and listening, guys.